So in number 9, you're looking at a one proportion z-test. It's a one sample, and we know it's quantitative because it's talking about weights, like pounds, right? And so it's a one sample t-test. So we're going to take our time and we're going to do phantom. Is there any evidence that US babies do not weigh the same amount at birth, right? That's important too. So P is really the question we just wrote down. Alternatively, they tell us that the hypothesis that we're looking at, like they're claiming that the expected weight is 7.41 pounds. Alternatively, right, they think that is our American baby newborns going to be the same as Australian, and so alternatively we're going to say it's not equal to 7.41 because it's just wanting to know if it's the same or if it's different. This example, if we look at our assumptions, we're looking for random babies. I don't think it's random, but we can expect it to be representative. They do tell us that if Missouri babies are fairly represent the American newborns, right? So that's enough to say it's representative. And then we have independence. This is obvious. Births are independent. And then we have 10%. We only have a sample of 112. So if we multiply that by 10, you end up getting 1,120. That's less than 10% of all new births. Less than 10% of newborns. Okay, and then we have the nearly normal condition. 112 is greater than 40, so we can assume normality. PHA N is going to be our one. Well, it's really just T test. That's what you find in your calculator. TO. The values we're going to be typing into our T test. Obviously, we have our average. Our X bar is 7.68. The standard deviation is 1.31, and my sample size is 112. The t-score, let's see, type this in, we got t equals 2.18. Our p-value is equal to 0.0313. My conclusion, I reject my null. Okay, my p-value is less than my alpha level, which alpha, in this case, we're going to let it be 0.05. We could say our evidence suggests if I can spell, suggests that American babies and Australian babies are not the same. Babies are, or you could say babies' average weights are different. Okay, so that's number 9. Let's move on. In number 13, you're looking at the ages of people who've had cardiac disease and people without cardiac disease. It's 2 separate groups, so we're looking at a 2 sample T interval, right? It specifically asks us to find a 95% confidence interval. And so we're going to use panic on this problem, right? So panic really is the P part's written right there. It's asking me to find Actually, it's probably more right here in the question. A, so we have random sample. It says that it doesn't say random, so we're going to assume that these are just representative of the population. Representative of the population. Randomness. Independence. And of course, lifespan is independent. Independent groups. Groups are independent. You're looking at whether they have a heart attack or if they haven't had a heart attack, so you've got very different groups. So the groups are definitely independent. You have 10%. So we have two different sample sizes. The mean age of the 2,397 and then 450. If we multiply both of these by 10, right, this is definitely less than 10% of all people with either heart attacks or no heart attacks. Right, you're talking about millions of people in both groups. That's such a big difference. It's probably not even really worth talking about 10% because it's pretty obvious that that's true. And lastly, we're going to have nearly normal, but this is nice because both sample sizes, right? Both sample sizes are greater than 40. So remember, when you have a sample size of 40 or more, we just get to assume that it's a normal distribution. Okay, and so we're going to be using a 2 sample t interval, and we're going to get our interval and go from there. So to type in, so I'm going to just put it in the order they give it to us. And so the mean age, so x average, x bar 1 is going to be 69.8 years. That's a sample size of 2397. X bar 2, almost forgot. Standard deviation there. Go back. So standard deviation for the first group is going to be 8.7. X bar 2 is 74, N2 is 450, and S2 is 7.9. So that's essentially what I'm going to be typing into my calculator. So we ended up getting, and we're using 95% confidence. So we ended up getting negative 5.01 to negative 3.39. Now, if you did this backwards, if your 1s and 2s on this side over here, if these were reversed, then you've got, you'll have the reverse of what I've got right there, which is totally just fine too. Okay, our conclusion will be I'm 95% confident that, let's see, I'm 95% confident that the average difference in lifespan for, let's see, I'm going to talk about the people without cardiac disease. For people without cardiac disease is 3.4 to 5.01 years less, that's because mine were negative, than those who have had cardiac disease. Okay, not what you expect, actually, but I think Part B kind of hits on that point here. Part B is going into and it's saying, how might an age difference confound these research findings about the relationship between depression and the ability to survive a heart attack? When considering the situations with the older you get, you are really more inclined to have health problems with lots of different things. And so if someone were to pass away as the older they get, there could be a lot of different things contributing to that death. It wouldn't just be necessarily cardiac disease or even depression. It could be a mixture of different things. And so making a conclusion here about B, or making a conclusion in general, would be a difficult thing because you can have a lot of different factors, and that's typically what they mean by confounding. All right, we're going to look at number 23, Legionnaires Disease. In this example, we're going to talk about whether mold has been reduced after an air conditioning unit has been changed out. They picked a couple of rooms from the hotel, and they tested the mold before and after the air conditioning unit was changed out. Because it's matched, because the same room has before and after, we're going to be using a matched pairs t-test, which really is just a single t-test in your calculator. So go ahead and we're going to do our normal alternatives, and our assumptions and conditions will come back. Okay, so here is all the other stuff. So I've got to the point now where, let's see, I set it up that I'm going to do the before minus the after. They think the before has the higher mold content, after's got less. So when I did that subtraction like this, that helps me to write my alternative. I think if I do before minus after, I should get a positive number, because I think the before is going to be bigger than the after, because they think that this part should have lower mold content. So if you subtracted the other way around, you would have chosen less than. So here we have mu d is equal to 0, meaning there's no difference, that didn't lower the mold content. That's what my null is. The alternatives is it did lower the content, and the after number is less than the before. So we'd say that this is a positive difference, right? So if this was like 10 and this is like 8, then I'd have a positive difference. It reduced it by 2, because this is too less than the beginning one. Random, we're going to assume that these rooms are representative of all the rooms in the place. We know that it's a paired data, because it's matched pairs test. 8 is less than 10% of all rooms in the hotel. When I look at nearly normal, remember I've put I put before in L1. I put that down. This is in L1. This is in L2. Right? So I did this in my calculator. L1 minus L2 equals L3. And so when I looked at L3, that's also the part what I'm going to do my test on. To do nearly normal, I did a normal probability plot, and what I want to make sure is that this graph is kind of a linear pattern. If it's linear, that means you got normal data. Okay, the next part would be to go into, so the name of this test is matched pairs. You could also call it matched pairs, matched t-test, paired t-tests. Any of those things are all fine. PHENT, test statistic, p-value, and then we'll write our conclusion out. So let's go ahead and calculate these numbers. All right, here is our conclusion. A couple things. It's matched pairs test. This is what I've typed into my single t-test. I use mu0, that was from up here. I use L3 as my differences. We got a t-score of 3.684 and a p-value of 0.003909. We reject our null because it's less than 0.05. Our evidence suggests that the mold content has been reduced, and that's 23. Okay, number 35. This one's about batteries, and what we're looking at is there's a company that claims to have its batteries last an average of 100 hours under normal use. They took a sample of 16 batteries and ran them till they died, and they wanted to know if that 100 value was accurate or not. And in part A, it says one of the editors who doesn't know statistics says that 97 is a lot less and they advertise 100 hours. Should we reject that company's claim? I explained to him the problem with doing that. The answer is no, you should not throw that away. A sample of 16 is actually a fairly small sample. And so we know that samples have different meanings. And for small sample sizes, you could see a fair amount of variation throughout the whole thing. So getting it 3 hours away from 100, I would think with a small sample like this would be fairly accurate. So it's definitely not something you should be worried about. In part B, the null hypothesis would be that the mean runtime of the batteries is approximately average of 100 hours. The alternative here would be they claim that it's not 100, that so bad if it does more, then that would be silly, right? They're claiming that it's less than 100 hours. Okay, in part C, we are going to check all the assumptions and conditions in order to proceed. So, randomness, we can assume that these batteries may or may not be random. I don't know if they mentioned that in the paragraph anywhere, but we can assume they're representative. Batteries definitely run independently. This 16 is less than 10% of all batteries at that time. Normality, now this is something we can't actually check. We can't really do anything about it, actually. We have a sample size of only 16, so that's not large enough. However, batteries have a normally distributed runtime. That may be a reasonable assumption, but in this case, we're simply going to say, well, I can't actually check it, so we're going to simply assume, and I'd use caution when I do that. Part D, it's asking us to kind of, basically what we're doing here is running through phantoming it just in pieces. This is a t-test. We ended up getting a -1 t-score with a p-value of 0.1666 and alpha level of 0.05. That result would give us we failed to reject our null here. We don't have enough evidence to say that the mean battery life is actually less than 100 hours. Okay. Part E. Part E is asking if at the 5% alpha level, if we made the same decision, which that's what we used, if the mean really was 98, in other words, it really was less than 100 hours, and we made a mistake, right? If we made an error, then what type of error did we make? Well, we failed to reject last time, right? So failed to, so we would make a type 2 error. We would have said that the actual average probably still is 100, when in fact that's wrong, and it was in fact less than 100. It was actually 98. So remember, when you fail to reject the null hypothesis, and if that's a mistake, you've made a type 2 error. When I reject the null, that's when we make a type 1 error. Hope that helped. If you have any questions, please feel free to post them on Classroom, or you can email me otherwise.